One of them is the position, one of them is the acceleration, one of them is velocity. So what the relationship is, if you have the position, the derivative of position is velocity. The derivative of velocity is acceleration. And the derivative of acceleration is, we'll call it j of t. I think, do they actually use j? Do you know? I don't know. So you want to find this relationship. So let's look at let's just pick one of them and look at what happens at a p. Let's look at A, for example. At A, what happens at that red point right there that I just dotted in? What's the derivative of A right there? The derivative of A is 0 right there. Do any of these other functions cross the x-axis at this x value right here? No. So what's interesting about this is, therefore, B, C, and D cannot be what in relationship to A? They can't be the derivative. You know that B, C, and D can't be the derivative of A. B, C, none of them can be the derivative of A. So what does that tell us A has to be, or A might be? A should be the what?
Jerk.
The jerk. Put a question mark, because I mean we're inclined to believe it. Let's look at B now. Let's look at that first peak for B right here. Do any of these cross at 0? Oh yeah, I'm sorry, it does. It's just my graphing is not very good. What does it look like? It looks like A of t equals the what of B? B prime of t. Do you see that, everybody? The rate of change right here, what's the rate of change right there? The only graph that crosses there, or really looks like it, is going to be A. So if A is the jerk, what does B of t mean? B of t is going to be the acceleration. Exactly. Are there any other nice peaks or valleys here? Not really. Doesn't look like it hits it. Let's look at C now. Does it look like C? What does it look like the slope is somewhere? It looks like somewhere in there what happens? It looks like here, somewhere around there, it looks like the rate of change is going to be 0. Kind of. Maybe. I don't know. How do we figure this out? What do we do? What kind of analysis do we do? Well, we found the jerk and the acceleration, so it looks like what's left, C or D, needs to be the position and velocity. So the derivative of C or D needs to be B. The derivative of C or D needs to be B. Well, let's look at D for. Let's just look at D for example. What's the slope of D? It's always what? The slope of D is always positive. What about C? Is the slope always positive? The slope of C is not always positive. The slope of C is not always positive. But the slope of D is. So whatever if D's derivative is there, it must be always above the x-axis. Which one is always above the x-axis? C is always above it. What about this one right here? Is D ever negative? No. So can D be the derivative of C? It can't. So therefore, by our own analysis, it looks like since D is always increasing, it looks like D prime of t looks like that's going to be equal to what? C of t. It looks like C is the derivative of D. So therefore, what does it look like? What is D? We think D is going to be the position, and we think C is going to be the velocity. So one observations we made that on this one right here, D prime of t is always what? Greater than 0. That was the key thing we observed at the end there. But we started by looking at the peaks and valleys. Peaks and valleys. Oh, dang it. Sorry. There we go. Peaks and valleys. There it is. Nice. Derivative. She's Lily. You are not Lily. We're using the y. Why are we using the product rule? The exponent has no. What does product mean? Two things multiplied together. What do you see up there? What's the first function? What's the second function? Exactly. So if you see two things glued together with multiplication, you have to use the product rule. So the derivative of the first is, what's the derivative of x? The derivative first times the second plus the first times the derivative of the second. What's the derivative of e to the cx? E to the cx times c. You have to use the chain rule right there. You're doing e to the cx. You're doing the derivative of that. So y prime is equal to e to the cx plus x times what? Ce to the cx. You have to do the derivative of the function that's in there. What's the derivative of x? It's 1, right? You use the chain rule every single time, but most of the time it's going to be 1. 1. It doesn't do anything. You never write it in. So we now have y prime is equal to e to the cx plus cx e to the cx. Nice. We now need to do the second derivative. How many derivatives are we essentially doing for the second derivative? 2 of them. We have 2 functions right there. What's the derivative of e to the cx? You already told me this. Ce to the plus, and we can just factor that c. That c is a constant, so you can just factor it out. What rule are we using still on this? The what?
The
Product rule, product, and then the chain rule. The derivative of the first times plus the first times the derivative of the second. We can clean this up a whole bunch. You get ce to the cx plus ce to the cx plus cx e to the what? Cx. How many ce to the x's do we have? We have 2 of them, so we have y prime is equal to what? 2ce to the cx plus cx e to the cx. Cool. Oh, double. Thank you very much. Yeah, it's the second derivative, second derivative, second derivative. Absolutely. Is that actually pretty similar to the first derivative? Here's the first derivative, and here's the... Do you want to make a prediction what you think the third derivative is? 3ce to the cx plus cx e to the cx.
You multiplied c by c, then you multiplied c.
Why did I multiply? Oh, there's a c squared. Thank you very much. I totally missed that. This should be c squared right there. Still, though, do you think you can make a prediction as to what you think the derivative is going to be? We think the third derivative is going to be 3c e to the cx plus c to the cubed x e to the cx. We predict. So therefore, what do you think yn is going to be? The nth derivative. N c e to the plus c to the x e to the... It would take a little bit to prove that. It's not that bad, but this is one of those interesting ones. Did it totally blow up in your face? No. Did it obliterate down to 0? No. It came out to something pretty interesting. That's pretty cool right there. I kind of like that. It's wrong. So we're finding the second derivative. To find the second derivative, what do we need to find first? The first derivative. Okay. So Patrick, tell me what's the if I take the derivative right here, read it across. What's it going to be? Plus times
y
equals
0.
yeah. If you got that far, that would be a great first step because you've conquered a few things. First, you need that y prime there because you're using what rule? Chain rule. You're actually using the chain rule right here. What's invisible right next to it? There's a 1 right here. Great. You are using the chain rule. It's just invisible. Now what should you do? Your goal is to get y, the second derivative. What should you do next? Absolutely. What can we divide by first, Devin? Oh, I'm sorry, Andrew. Sorry. And it's on tape, too. I apologize. Yeah. Divide by 4. Simplify. Take what it gives you. X cubed plus y cubed y prime equals 0. So what does y cubed prime equal? Negative x cubed over. Nice. Okay. So what do we take now? The derivative. Again. Is it implicit or is it direct differentiation? How do you know you have to use implicit right here? You have x and y. Is that a function? I don't think so. You have an x and a y. So let's take it. What rule do we have to use right here? The quotient rule. Are we too picky about using the quotient rule?
No.
You should always get a little bit, but is there any way around it that you can see? Not really. I mean, is there any cool simplification you can make? Is there any like trig identity or random thing? No. So you have to use the quotient rule. You're going to have to. Yeah. I mean, you're technically using the chain rule all the time. I understand what you mean, though. You're going to have to pop out a y prime again. So what's y double prime here? What's low? Low is low d high. What's the derivative of the top? Low d high minus high. Can someone tell me the derivative of the bottom? Y prime all over what? Y to the to the 6th. So here's the thing. This is technically y double prime. There is one thing in there that I don't like, though, that I want to get rid of.
Y prime.
I do not like y prime. Well, do we know what y prime equals?
Negative x cubed.
Y prime is right here. It's right there. So what can you now do? You can entirely write this in terms of x and y. So our final answer is going to be y double prime is equal to negative 3x squared y cubed plus x cubed, well, 3x cubed y squared times, what is y prime again? Negative x cubed over what? All over? If I gave this to you, that would be technically correct. I would expect you to do a little bit more simplification, a little bit more. Not much. You don't need to do y double prime is going to be equal to negative 3x squared y cubed minus what? 3x cubed to the what power? Negative 1 all over what? Y to the 6. That doesn't change. Why is it y to the negative 1?
Why is it 3x?
It's not x cubed. It's
3x to the what? Thank you. Why is it y to the negative 1?
because y is squared over.
Because it's y squared over y cubed is y to the negative 1.
It's the same thing as y squared.
Yeah. Are there any, can you simplify this a little more maybe? Yeah, I mean, again, what class is this? You don't need to do the algebra unless you have to. For example, on the AP test, they might give this to you and say, what is the second derivative? Will they give you this as like one of the multiple choice answers? No, they will not. What will they do? They will simplify it down. They will keep going. They will absolutely keep going on this. They might leave it right like this is where I guess they'd leave it. That's the reason you would simplify. You'd also simplify maybe if you had to do something else, like find a maximum or a minimum, which we're going to learn all about soon.
So why could they simplify even more?
So what do you do for 29? What do we have to find first, Carter?
First derivative.
Yeah, so can you read me, what do you get after you do the differentiation?
18x plus 2y.
2y prime equals? Yep. So what does y prime equal? Negative 9x over y. Now what do you use? Y double prime is equal to low d high minus high d low all over y squared. Do we know what y prime is equal to? Y plus 9x, negative 9x y all over y squared. Can you simplify that a little bit? Y double prime equal what? Negative 9y minus what? 81x squared y to the all over y squared. There it is. Let me show you one different way to think about this. Another way to think about this is, another way to think about this is you do the first derivative exactly like you did before. Let's do the first derivative exactly like you did before. You get 18x plus 2y, y prime is equal to what? 0. 9x plus y prime is equal to 0. All I did, what did I do to get from that line to, from the last line to that one? Divide by 2. Here's the thing. Do we need to absolutely isolate y prime in order to take the derivative? Did we have to isolate y to take the derivative there? So do we have to isolate y prime to take the derivative here? No, we don't. So let's take the derivative. What's the derivative of 9x? 9 plus. Now what rule do we now need to use? Product rule. What's the derivative of the first? Y prime times phi prime. The derivative first times saying plus. The first times the y double prime equals. So what does that equal? 9 plus y prime squared plus y double prime equals 0. Now this works, it's just going to be a little bit more, it's different. What do we isolate now? What are we looking for? So y double prime is going to equal, well let's just do this. Y double prime is going to equal what? Negative 9 minus y prime squared. So y double prime is equal to negative 9 times minus y prime squared all over what? Now here's the thing, what do we need to get rid of? So what do we have to isolate for anyway? Yeah, so you do this, then you end up with y prime, so you still need y prime. This is just another path you could take if you wanted to. You could. You don't have to take it. Let's look at this second question right here. It says find the nth derivative, the formula for Fn. So how do you start this? What do you do first? And then find the y. Why do you find the first few? To see a pattern. So you get 1/2 x to the, then you get f double prime of x is equal to negative 1/2 times 1/2 times x to the what? Negative 3/2. And then you get f triple prime. And should I write 3 marks like that? What should I write instead? f3x is equal to, now is it turned positive or negative here? So it's going to be 1/2 times 1/2 times x to the negative what? 5/2. So f4, let's do one more, equals, is it negative or positive? Back to, why am I not multiplying this all out? Easier to see a what? X to the negative what? 7/2. Awesome. Okay. So let's see if we can find a pattern here. Or we can describe what's going on. Let's do the easier part first. Let's link the 4 in this power right here. What's the denominator of the power always going to be? It's going to equal something, x to the over 2. 3 went to negative 5, 4 went to negative 7. How do you get this? We negative what? 2n minus 1. What's 2 times 4? 8 minus 1. 3 times 2? 6 minus 1. 2 times 2? 4 minus 1 is? So we just did the power. Let's do the second easiest thing. What happens to the overall sign of this function? Yeah, it switches back and forth. It goes from positive to negative. Which ones are negative? The even derivatives, even number derivatives, or the odd? Well, you know if it's going to switch, what do you have to be in there? Negative 1 to a power. What power do we raise it to? Just n. Because what's negative 1 to the 4th power? 1. What's negative 1 to an odd power? Negative. So this is the proper thing. What? Oh, no. 4 goes to negative, so what do we need to make it? N minus 1 or n plus 1? Which one do you think I put in there? I like putting plus 1 in there just to minimize the number of negative signs I put in places. You're absolutely right. What? Ah, you're well, no, hold on. If the first derivative, if it's 0, so you're saying, does it work with f0? So, like, we're saying, so negative 1 to the 0 power is what? Oh, no, you plug 0 in. Okay. Well, let's build it. Hold on. Well, it'd be the 0th derivative. We don't really have that. You would think that maybe be the original function. So for this one, let's just see if it works here. When you plug in 2, it should be negative. Is it negative? Yes. Let's just go with that for now. We'll come back. So the middle part, that's the challenging part. What are we modeling here? It's this thing right here. What part of that fraction looks like the easier part, the numerator or the denominator? It looks like the denominator, because what's the denominator always going to be? Not a multiple, what's a better way to say it? It's not a multiple of 2, it's a, be more specific, a power of 2. It's a power of 2. When you took the second derivative, what was the power of 2 in the denominator? There were 2 of them. When you took 3, there were, when there were 4 of them, there were 4. So it's going to be what? Over 2 to the n. Good. Now, look what products we have. 1 times 1. We have 1 times 1 times 3. We have 1 times 1 times 3 times 5. So we have 1, we have 3, and we have 15. What's the next one going to be? Well, the next one's going to be 1 times 1 times 3 times 5 times, so 15, what's it going to be? It's going to be 35. 7 times, no. It's going to be what? 105. So look what we have here. We're trying to find a relationship between, here's the second one, here's the third one, here's the fourth one. And what numbers are we now looking So 2 goes to 1. 3 goes to 3. 4 goes to 16. And then the fifth one, what does the fifth one go to? Fifth one goes to 105. This is where it gets a little bit more fun.